Take a classic dynamical system like the Collatz conjecture. It generates a hailstone sequence of numbers that bounce wildly, following no apparent architectural rules. Because these sequences can wander infinitely without ever returning to a previous state, mapping their long-term path is practically impossible. You are staring into an endless horizon. There are no reliable structures to grab onto, and no predictable landmarks to guide the way. As long as a mathematical sequence operates without boundaries in an infinite space, it remains an unmappable void of pure chaos. We can change the environment by forcing the numbers onto a closed, finite track. This diagram illustrates the modular clock. By applying a specific limit, known as a modulus, the sequence is mathematically constrained within a strict boundary. Shifting to this fixed domain changes the objective. We can now search for the exact resonance between 3-adic expansion and 2-adic reduction that allows a mathematical path to close. To identify these closed loops among millions of possibilities, we apply a constraint called the cooling rule. This diagram shows a modular wrap. When a growing sequence exceeds the modulus, it overflows and resets lower. This reset forces the value into the lower half of the space. It cannot hit the ceiling again on the very next step, requiring a cooldown. The sequence is a balancing act. It requires upward growth to counter downward reductions. If a path consists of more than 36.9% downward steps, it loses momentum and eventually crashes. Enforcing this geometric speed limit eliminates over 80% of all theoretical paths. The mathematical noise clears away, leaving only stable, oscillating candidates. Now we have a refined set of Lucas-admissible paths, sequences that obey the cooling rule. That we still need to prove which ones connect perfectly from start to finish. To do that, we use a procedural filter called the 6-step automaton test. This visual shows the internal mechanics of that test. It models the sequence as a tug-of-war between two opposing forces, mathematical expansion and mathematical clearing. By treating the sequence this way, the test acts as a scale-free map. We can calculate exactly if a cycle perfectly closes without needing to know the precise dimensions of the track beforehand. The simplest loop to pass this test occurs at length 3. It creates a smooth, continuous circle with a single predictable wrap at the end. The automaton test acts as a mathematical verification. It confirms that a theoretical alignment calculated strictly on paper corresponds to a valid repeating orbit within the modular space. As we scale this test up to longer sequence lengths, lengths 4, 5, and 6, the system continues to output stable, smooth, single-wrap circles. But at length 7, these simple geometric rules break down. This threshold is the structural bifurcation point. It marks the moment a sequence splits into distinct behavioral families. At length 7, the system's internal expansion becomes powerful enough to overwhelm the simple boundaries that contained the lower periods. Past this threshold, new geometric shapes emerge. We find non-canonical multi-wrap paths that follow much more complex itineraries. This diagram shows the complex new geometry. It's an asymmetrical sawtooth pattern, defined by an irregular pulse of shifting reductions and growths. As we scale to lengths 8, 9, and beyond, this geometry branches endlessly. Extreme complexity is the rule. By forcing chaotic infinity into a finite boundary and filtering out the impossible, we find the structural blueprint underlying one of the universe's most unpredictable sequences.